going to be a quick overview of the low power, that is the power down modes that we integrated in the gem5 memory controller. And we did this together with colleagues from University of Kaiserslautern, and Matthias is here in the audience. You can give a quick wave. So getting right into it, a quick background on DRAM in gem5. So the memory controller is a component which is on the same chip as the processor typically, and it interfaces with the off-chip main memory, which is of a DRAM type volatile memory. We receive, the memory controller receives packets or requests from the system interconnect. The memory controller receives requests from the system interconnect and then sends read and write commands to the DRAM on the off-chip channel. And these read and write accesses, the data that is stored in DRAM is organized in the form as ranks, banks, and rows and columns. So each bank is made up of rows and columns. And this organization, as well as the timing constraints that are associated with retrieving the data, are specified by the DRAM device manufacturers. So that's why I've shaded them in the yellow color. Now, one thing to remember for the rest of the talk is that when a particular data is accessed from the row, it is brought into a row buffer, which is also known as a page. And that's when we say that the bank is open. That's when we open a row and we bring it in the row buffer. And when we put the data back into the DRAM, we pre-charge the row, and we say that the bank is closed. So this is some terminology. Now in gem5, we also have a DRAM power tool that's shown on the very top here. And this is a component that is non-invasive but does a lot of useful things for us researchers. It takes in as input the command trace with timestamps and calculates the energy consumed by those particular transactions by plugging in the currents and voltages, which are again something that is specified by DRAM manufacturers. So one other thing to note is that the memory controller implements a state machine in order to correctly communicate with this DRAM interface, and that is based on the specification coming from the JEDEC standards body, and that is something all controllers have to obey the strict command sequences and timing constraints. Now diving deeper into the memory controller. So going first into the basic states. These are the power states, and I'll go quickly through them. The active state is the normal operating state of the DRAM when it's able to service requests. And in this case, it's defined as at least one bank of the DRAM must be open. The next state here is the idle state, in which all the banks are closed. So they are all pre-charged and all banks are closed, but this is also a normal operating state. And the following two states that I've listed here are the lower power or the power down states. The active power down corresponds to at least one bank open, and the pre-charge power down is all the banks closed. But remember that the currents consumed by these two are lower than the active and idle states. So they help us to have an energy efficiency in the memory subsystem. Now the DRAM, as most of us will know, is a volatile memory, and the charge on the bit cells needs to be refreshed periodically in order for them to carry the right data. So the DRAM controller's responsibility to issue refresh commands periodically. And the last state here, that is self-refresh, in this particular state, the DRAM controller does not need to issue any refresh commands. This is a deeper power down state in which there is internal self-refresh, and the DRAM does the refreshing in a much more energy efficient way. So one thing now for designers of memory controller. The power saving potential of the DRAM depends on how long the DRAM is put into a power down state or a self-refresh state. But it also takes some delay to exit from the power down state. And therefore, we are presented with a trade-off here, the power and performance trade-off. And so there is an optimal time and there is some decision making involved in when to enter and when to exit. And this is where our contribution comes in. So late last year, we contributed code that adds entry and exit control logic to the memory controller in gem5. And with this, we now integrate the power down modes into the memory controller. And after a gem5 simulation, we get statistics for the breakdown of the energy and time spent in the different power down states. And therefore, if any of you would like to do changes in some sort of execute early and go to sleep kind of strategy, for example, you'll be able to see the lower energy consumption from the DRAM subsystem because of these changes. We also have written a paper describing all the low-level details, and that will be published in MEMSIS this year. So I would encourage you to come talk to me later or refer to this paper for all the behavioral characterization as well. So the memory controller does some other functions, right, like scheduling of read-write requests, as well as different kinds of page policies. For these, I would refer you to one of the earlier papers in ISPAS 2017, which talks about or the broad function of the memory controller in gem5. Now, getting to the meat of what we added, the scheduling of power down states. So what is the conditions that we check in the controller to decide entry and exit? So really glossing over some of the details, but the main thing we did is, if there is no activity in the DRAM, that is, the queues are empty, the request queue is empty, and there are no pending events. Examples of pending events are a refresh operation or a pre-charge, impending pre-charge. Then we decide to go into a power down state. And because gem5, one of the main things about it is that it is event-based, so we can really have faster simulation. And there are trigger events at which we check these conditions. And those triggering events include a start of refresh, end of pre-charge, or when we respond to a request. And that's when the state of your memory controller traffic changes. And that's when we should try and see, hey, is this a good point to go into a power down state? So we also implemented an optimization based on the staggered power down paper that was already prior art from our colleagues at University of Kaiserslautern. And to quickly go over the timing diagram here, the y-axis shows power. So the red line is showing you the power taken in by the system. It starts with the DRAM being in an active state, and at a refresh operation, we detect that it can go into a power down state because the conditions for power down entry are satisfied. So you can see that the current suddenly drops. It goes into the PDN-A. Now, our trigger condition is the refresh operation. So we wake up on refresh. We do the refresh. That means we pre-charge all the banks. We close it. And the ref-A is, you can see it shoots up. That's the higher power taken during refresh. At the end of the refresh, we say, oh, OK, there is still no activity. There are no requests. There are no events. Let's go into the pre-charge power down state. Now, subsequently, there is again another refresh. And because we have already been in a power down state, we decide to go into the self-refresh. That is a deeper power down state. But notice here that just before the dark gray region, we did not do an actual refresh operation. We skip the refresh operation because the first thing we do as we enter the self-refresh is a mandatory refresh. So without this optimization, you end up sometimes having higher energy consumption while entering self-refresh because you entered self-refresh for a very short time. And to avoid that, we avoid back-to-back refreshes because of using this strategy of skipping the actual refresh operation between the medium gray and the dark gray. So this is all described in the paper. Now, finally, does this work? What is the impact on the energy and performance numbers? On the left side, you see some plots showing the breakdown of energy consumed, which is now possible because of the code we added. And this gives you really good detail on where the time and energy is spent. Just one highlight here on the left side, as you see the yellow portion, which is the self-refresh energy. As we spend more time in self-refresh, the refresh energy goes down as well. And this is because external refreshes are not needed anymore. And finally, some numbers on the power performance trade-off. This plot shows some HPC workloads on the x-axis, and the y-axis shows the light blue bars are percentage increase in execution time, that means the performance degradation, and the dark blue bars are the percentage energy savings. So you can see that there's no free lunch. As soon as you start to have some energy savings, you're going to affect performance in some way. For compute-intensive workloads like FFT or DGEM or LinPack, the power savings can be as close to 14%, and the performance impact is quite small. It's just between 3 to 4%. So these are some numbers that show that our model works. So the characterization, as well as an experiment of before committing our code and after committing the code. So just to conclude, DRAM is a major energy consumer in systems. And with this, we would encourage you to have richer full system energy efficiency studies rather than focusing on smaller subsystems. And I'd also like to thank my colleagues, Wendy and Andreas at ARM, and Matthias and Kristen and Norbert at University of Kaiserslautern. So I am open to questions if we have time.